this talk, I want to share with you our attempts to automating data science workflows within BBVA, and we are, as Pete said, the data science branch of the banking group BBVA. We are a young company. We exist since 4 years ago. As Pete said, we are 50, 60 people working in Madrid and Barcelona. And as a young company, 4 years ago, we went from doing zero data science to delivering big projects into production at the scale of BBVA. So we were able to do a few loops of real projects and growth, and we've learned a few things, okay? And one of the things we learned is that the data science processes or workflow, the way of working, also contains some inefficiencies. And we, it's not so surprised probably, and we actually ask ourselves whether this can be addressed with some data science tools also, okay? So this will sound a bit experimental, and just a caveat here, we have data scientists and data engineers, but so far we've been a bit data science first, okay? And this is changing, but this will explain that if some parts of this slide sound a bit experimental to you. Okay, so as in many other companies, the goal of data science and data engineering teams is reducing inefficiencies in products or services, okay? And more concretely, to us, it means things that we can show through real examples. So these are real projects that we've been working on and where we delivered something into a product. So one of the first projects, as in any data science teams that goes to a new domain, is, guess what, recommender systems, right? So we've been working a few years in recommender systems. The interesting thing in recommender systems for banking is that you can do things like here. Customers through the app could receive discounts, and retailers who are also customers of the BBVA retailing or BBVA enterprise can connect to their dashboards, and it would be great if there is a way to match retailers with relevant customers. So we've been working on building recommender systems for that. We've been using standard tools like collaborative filtering, but also easily we found there's a data engineering challenge there, as we have more than 10 million users and 1 million products. So here in this blog post, you can also read about a talk we gave at the AWS Summit explaining the details of how we made this efficiently, right? And also behind that work, there's even some research in recommender systems that is going to conferences. So this is an example of end-to-end project which have a clear business benefit and which has challenges both at the data science and data engineering level. And when I say that this helps reducing inefficiencies, it's because now it provides a new way to efficiently connect retailers and customers, which before was not possible, or it had to be done through other channels, which involves maybe rule-based systems or expert knowledge, right? So this is an example of an inefficiency that is reduced in the back end. We also working to reduce inefficiencies in the front ends for customers. So I don't know how your bank displays their website, right? But since a couple of years ago, we've been proposing to display the customer expenses in experimental ways or more meaningful ways. And this is an example where customers can browse their expenses by categories and navigate not in chronological order, but in, let's say, semantic order. So this required building a text classification and transaction classification system, which is running behind that product that is now available for all the customers in Spain. And we had a talk at the last Spark Summit Europe, where we described some parts of that, some challenges and some research we were doing there. In the same way, 1 year ago or so, we had released the forecasting expenses tool, which helps customers, it alerts customers about potential upcoming expenses they were not aware of or they were not remembering, right? And this is a machine learning system that is running behind this product that is analyzing the time series of customers and doing forecasts. And in this particular example, we are especially proud of that because it's really a machine learning-based system. There is no single hard-coded rule there. Okay, again, this is helping reducing inefficiencies for customers because customers can be remembered automatically or don't need to go with a calculator, and this is really helping them. Okay, and just to show you how complex these projects are, this is not only data science and engineering, but the specific problem of time series forecasting is actually has also many open challenges in terms of the analytics or the science, and we've been also working sometimes in collaboration with universities here in Barcelona to actual research in time series forecasting in order to generate knowledge or new models that later could be integrated into those solutions. So this is an example also of research that we presented recently in the European Machine Learning Conference. Okay, so these were 3 examples, end-to-end projects, pretty challenging in terms of data science, data engineering, even science, and which were delivered in some way to the business. And the thing is, okay, yes, we helped reducing inefficiencies, but over the years working in those, in this context, we also learn that the workflow of data scientists when they work on these projects also has inefficiencies themselves, right? And as I said at the beginning, I don't think this surprises you. Everyone who is new to the field and goes into data science reads things like that, right? You know, cleaning big data is the least enjoyable data science task, or feature engineering takes 90%, you know, all these typical statements, right? But the thing is it true? So we wanted to answer that question, and actually we made the effort to document the workflow of data scientists in our project. So this is a slide which has been actually compiled by data scientists. It's not a communications slide or a management slide. So this was actually compiled by data scientists who wanted to make their work fit into the processes of large corporations, like, you know, if you have to be compliant with agile practices, how do you mix the 2 worlds, and so on. So this is actually how our data scientists describe the steps they do in their projects. Okay, so if you're in the data science business, you may have similar processes, or you could adapt that. I think you would agree on most of the ordering of starting from business understanding, proposing analytic approach, then doing all the data work, data collection, gathering, data engineering, feature engineering, right? Then feeding those features into models, evaluating these models, and maybe going back if the model is not satisfactory, and eventually deploying, and later, if you are lucky, having customer feedback, which can in turn you know, produce other loops here, okay? So this is what our understanding is from data science project. And there's a lot of complexity in many places, so these arrows here are here because, so data science is and the feature engineering is a very manual process with lots of unknown unknowns, then investigating, looking at the data, discovering new things, and slowly building the best features for a given problem, right? So our question is, can we actually, with our data science, can we help improving at least some parts of this workflow? And this sounds, as I said at the beginning, a bit experimental, but you know, there are people who have thought about that also in the past, and you know the typical examples, like products such as Google Cloud AutoML, which is aiming at also like automatic hyperparameter and model selection, or the Teapot open source code, where you can define data science pipelines and let a genetic algorithm automate them or find good models. And on the right, you see a couple of research projects which are aiming at either automatic model selection or the one from MIT, which is about finding combinations of attributes automatically from tabular data that will be the best ones for a given prediction, you know, use case. So looking at this, this is a bit the context of what I am going to explain. I'm going to explain a couple of real projects, real attempts to increasing the efficiency of our data scientists by providing them tools that are created with data science. Okay? Here I make a parenthesis. In these 4 years, we've also learned that if you want to make data science more efficient, a very good way is to also invest in better engineering practices and better engineering tools. Okay? And we are doing that. But this is not the subject of today's presentation. But if you want to discuss about that, we are happy to discuss. And our CTO is also here, who can give you insights on this topic. Okay? But here we are going to show 2 specific projects for increasing data science efficiency. The first one is what we call client-to-back, and the goal is to build systematic baselines to make them available to data scientists, so that they don't have to start from scratch in every project. So here we meet again our workflow. Let's remove a few things just to concentrate on the line between the business initiative and the evaluation. So when I said systematic baseline, what I mean is the following. Can we find some way of shortcutting this? Is there a way so that we can save, at least at the beginning, save this path here and have maybe some set of standardized attributes and a standardized model, at least for a given set of narrow situations where we can do that, okay? So it turns out most business initiatives, so the business initiatives can be very varied, right, and can be a lot about many things. But the majority of business initiatives are around a limited set of entities, right? For example, Spotify works with songs and users, okay? So we work with users and products. So it turns out in many cases, a new business initiative is about predicting some property for a customer. And in order to avoid starting from scratch and doing all this path every time, we could have, for instance, a set of standard customer attributes and a set of standard models, so that at least the data scientists can go through this path once and very quickly. Then maybe learn something from doing that. And yes, I agree. Then the devil is in the details and you still have to go through the other part. But at least doing that could give some benefit, right? So I'm going to explain you how we did that. So for us, a systematic baseline is 2 things. First, a generic representation of your entities of interest. And here we started concentrating about customers, as I said, because most of the business problems are about predicting a property of a customer. For example, segmenting a customer into a group, or recommending a product to a customer, and so on. So there you need to have customer attributes. And then the second part is a flexible and simple model to use with those attributes. So you will have the question, like, is this possible? Do these things exist, right? Do these generic entity representations or flexible models exist? Well, in some situations, yes, they do exist. For instance, I was reading that Spotify pre-computes song embeddings. So as you know, embeddings is the ML, machine learning jargon, technical term for a vector representation of an entity. So Spotify is using song embeddings pre-computed so that other data scientists can benefit from those and use them in their projects. And in general, there are many situations in machine learning where researchers have found that, yes, these generic attributes exist. For example, in NLP, you can have many NLP tasks. I don't know if some of you are working in NLP in your project, but you can work on document classification or entity recognition. But today, a big amount of the projects using NLP for different purposes have these pre-processing steps of computing word embeddings. And there are very standard techniques to do so, okay? As you may know, word-to-vec is a method to assign a representation of a word. Okay? Here the word is your entity of interest. That then has good properties to be used downstream in other processes, okay? And one well-known property of word2vec is it will assign a vector, an array, okay, of numbers to a word, such that if you compute physical distances between the elements of the array and then project them into some sort of visualization that preserves those, you would find that related words in meaning will appear closely together. Okay, and here you see two examples. This is some word cloud we computed for this presentation. And here you see there's a region of the space which contains the auxiliary verbs. There's a region of the space that contains the words relating to location and so on. Okay. So we want to get inspiration from this in order to construct our generic or systematic baselines. And in our case, it would look like the translation of the previous idea to here would look something like that. So you have to start with a raw representation of the customers, then try to convert these into the generic attributes I mentioned through some machine learning method. And as I just mentioned previously, you can think of that, or you can interpret that as a point in a space in some way, which I'm going to detail later. And then we found that there's this very simple but very effective classifier, or in general regressor, called nearest neighbor regression, okay, which is flexible enough to work in every problem as long as you have enough data, right? So let's go through these steps. So first, raw representation. So by raw representation, I mean, and this is my definition, any information that you can get from your data sources using a sufficiently simple query, okay? So if it's more complex than, so if the query needs to be complex, it's not raw data, right? So here I'm showing an example where I say, give me the accumulated expenses for each customer for the last year and grouped by categories, okay? And this will be my, what I call the raw data. So of course you could also, you could already do interesting things with those raw data if you want to segment customers or predict things. But it's always more interesting to find a representation that captures some of the semantic properties of this data. For example, you don't know if one category is more important than another category in terms of defining customer behavior, right? Or another situation is that many times you observe a zero expense, and then you don't know if the customers really had no expense in that category, or it's not going through your bank, right? So this could happen. So this is the raw data. We will transform this raw data using a neural network that performs a conversion of this raw data to an array of values that has this property that two similar customers will be assigned two very similar arrays. Okay, so that this is a good property for, this is a good general assumption for whatever machine learning method you want to apply later on. Okay, and I will discuss the model in the next slide. But basically you can understand it as what means two customers are similar. It means you can predict the expenses of one with the expenses of the other. Okay. And finally, we found that this is a very good pattern when you combine that with nearest neighbor regression. So if you have enough pairs of X and Y, meaning of customer attributes and the label of your task, and you have enough data, you can always perform a nearest neighbor regression on almost any task, right? A nearest neighbor regression goes like saying, if I want to infer a property, an unknown property of a customer, I find the most similar customers where the property is known, and then do some operation like averaging, for instance, with that property. And this is a quite generic baseline that we found it's, it's applicable to many problems. Okay, and I recall this may not be the best solution for all the possible tasks, and I'm not claiming that. So this is just a very, once you set this up, this is a business that can be run very efficiently in the early stages of a data science project. Regarding how we compute the representation, and here this is a bit going in depth technically, but if you're in machine learning, I'm sure this concept will be very familiar to you. So we use a denoising autoencoder. So an autoencoder is a neural network, and as you know, in a neural network, you can have some inputs. Here our inputs are the dictionary of raw data, as I was calling it, and then it performs an operation which yields an array of values in another layer. So this array of values is obtained by multiplying those input values by some coefficients. Okay, then you get another layer. You can do the same and get another layer. Okay, and an autoencoder is basically a network that learns, we could say it in simple terms, learns to predict some of these. So learns to predict the value of one input given the other inputs. Okay, more or less. This is more true for this type of autoencoders called denoising autoencoders. So in denoising autoencoders, you artificially put some of the input values to 0 while you are training. And this is simulating the situation I mentioned before, right? Maybe a customer had a 0 expense in a category, but it's not because they didn't make an expense in that category. It's because you didn't observe it. Okay, example, if a customer has expenses in garage, right, it's almost for sure they have a car, but they may have an insurance with another bank. So your insurance would be 0. And still you would like your method to capture the information that they may have some expenses in car insurances. And these methods are able to achieve that. So it's also theoretically been shown that when you input these values, the values you have here in this hidden layer have the property I'm discussing before, right? This is an array of values that represents your entity, and 2 similar customers should have 2 similar arrays. Okay, this is what we are using. And in fact, later we found that a variation of that called marginalized and stack denoising autoencoders is the best method to perform these things. Okay, here I'm showing, after each train, I will show an example of what is it doing, okay? So here the rows corresponds to customers. The columns, you see a white or black square, and it corresponds whether a customer had or did not have an expense in one of the categories. Okay? For example, one of these columns means supermarket, another column means school, another column means withdrawal from an ATM, and so on. Right? And you see here a few customers, and you see if during a year they made or did not make that action. And here we have, this is not visible here, but we have made a clustering of those customers. And here, each of these blocks is one of the clusters. And to do that clusters, we have left out the hotels category. Okay? To make that clustering, we did not take into account whether the customer went or did not go to a hotel. But it turns out when we inspect the clusters that where the travel expense is active, which is, I think, this red, one of these columns here. I cannot remember which one it is. But so one of these columns means the customer had an expense in hotels. We took all the clusters where customers have expenses in hotels, in travel, and we found that they appear to also have expenses in hotels. So it has clustered correctly, we infer, people with traveling behavior. Okay? When we compare to the traditional sociodemographic attributes that are used in banking for campaigns or for segmentation, we find that when we inspect at those clusters, the clusters don't have a meaningful interpretation. And this is because like 2 people of the same age who live in the same postcode could have many different expenses in different categories and thus different behavior. So we've written some of the findings in this paper here that we invite you to check if you're interested. Just to summarize, we did 2, let's say, main use cases. One was client clustering. So the idea would be to replace the classical segmentation in the bank by segmentation by behavior. And here, comparing to other methods, our clustering quality metrics improved by 61%. And the other use case was category prediction. Like can we predict if a customer will have an expense in an unseen category? For example, will the customer incur in opening a savings account, right? And this could be interesting for recommending products. And again, on this benchmark, we had an improvement of 76% with respect to the baselines. So for baselines, we use baselines with socio-demographic attributes, also using the raw data without any processing. And this was the summary. This is still an ongoing project, but internally, we are trying to address this project and align these projects with 3 pillars, which are research, implementation, and product enablement. It means we are taking care of the 3 of them at the same time. So it's not a fully research project, or it's not fully a development project. So as you see, there was algorithmic research here, because we had to find a good way of representing customers in a generic way, which conforms to the state-of-the-art methods in machine learning. We have implemented that as a software package, which is available to our data scientists, and we've done it in a way that it requires lightweight training and that it can work on our own infrastructure, and it's really relatively lightweight to use. And then during the development of that project, we have been paying attention to use cases, and we were aligned with some business unit to start to have early feedback on whether this would be interesting for the data scientists working on those projects. So as I said, this is ongoing work, and the main metric here of success will be reusability, right? Is how many different projects use that and go down this path that I mentioned. I'm going to show a second example of a project that we call Automatic Modeler. I will go much quicker over this one, but then if you have questions or are interested in general, we can discuss later. So the Automatic Modeler is it's a different situation. It's a situation where you have where you need to construct end-to-end linear and interpretable models, and we've designed a pipeline to do actually this end-to-end design of features and models, so that basically data scientists don't have to do manual feature engineering. And again, here you meet the workflow again. As we said, there's this chain from business understanding through data, through model to evaluation. And of course, you can never automate that. You can never claim that you can automate everything here. Why? Because there's a lot of manual work here, human decisions, unknown unknowns, so it's not possible, okay? But if you constrain yourself to very narrow situations, which you identify that repeat over time, then it's possible that you can identify specific steps here and propose automations. And this is what happened with this project here. So it turns out in our data science projects, we met very frequently this situation. You need a linear model, okay? You need to have few variables, and you need that the variables are interpretable, okay? So what does it mean? It means you want a model like this, you know. The probability that a customer buys this product is coefficient times the balance in the account plus another coefficient times the days since, you know, last product plus another ratio of this and this variable, okay? So you need this for different reasons. Sometimes these models are given to domain experts, people who are domain experts but not experts in machine learning, so they have to be able to understand what the model means. Also, this is because in some cases this is given by the regulation. So the regulator forces that you have to use an interpretable model. So the situation here is a data scientist or an analyst would explore many feature combinations, start trying, propose a feature combination, evaluate it with their model, check the accuracy, then invent a new feature that they think it's meaningful, and so on. Okay? So here we built a pipeline that will emulate that behavior from a data analyst, and actually will produce models by itself, and has a, you know, can self-check the quality of the models, and at the end propose a set of a diversity of models to an analyst to do the final validation, okay? And very briefly, this is as follows. So typically, you have raw input variables for a customer, right? Socio-demographic variables, expenses in categories, and things like that, right? We typically start in those projects with a few hundreds of variables. Then, simulating also what some analysts would do, we perform a variable expansion. That means we convert all those variables to new variables. Okay? How? So we can apply transformations of those variables. For example, it is well known that when you deal with monetary amounts, the logarithm of the amount behaves better than the amount. So, okay, let's try a few functions here, logarithm, squared, and so on, and also feature combinations, like one feature minus the other, or ratios of features, okay? If you've read, if you're on Kaggle and you have read Kaggle forums, you will see that the data scientists really do that. They say, oh, I found feature 347 minus feature 286 is the best predictable feature, right? And so here, why don't we define, let's say, a primitive or a dictionary of possible combinations, and then just compute all the combinations. So we are here. That will produce about 250,000 features, okay? And of course, most of them are meaningless. We can easily check when a feature is really not correlated with the target label with a statistical test. So the next step is a statistical test where we can reject 1/4 of the variables or so, or 1/3, and get up to 80K, okay? And now we have variables, which are our candidate variables, but one problem here is they don't provide a lot of diversity. So many features are very correlated or mean almost the same. So what we do is, in the next step, we do a hierarchical clustering of the features. So we cluster features by the correlation they have between each other. So this produces groups of features that more or less mean the same. And this produces about 1,000 groups. And then here comes now the real step of building the model. With these 1,000 clusters, we can select a proxy of each of those clusters. That means a variable that represents the cluster so that you don't need the other variables. And let's say you have to pick up to 10 variables of them, which are not too correlated, and check what is the accuracy of picking those. And in order not to do all the combinations, because it would be impractical, we combine two mechanisms, one SFS, which is a feature selection algorithm, to make an initialization, and to find a set of possible variables that are meaningful, and then a genetic algorithm really does the selection. They select a group of variables, evaluate it, check the accuracy, then select a different group of variables based on the previous result, okay? So that you don't do combinations blindly, but combinations guided by what you already know, okay? At the end of the process, you have something like that. And this is a real screenshot of the UI that comes with this internal tool, okay? You have here a table of candidate models, and you say model ABC. You can give names to the models if you want, but here for the example, it's just letter names, right? And it says how many variables do these models have, here from 1 to 9. This is actually, let's say, it's actually a single model, but all the combination. So the model with 1 variable is considered different from the model of 9 variables, okay? But you can explore other models. Here you would see what is the accuracy of each of these models as a function of the number of variables. So as if you want to find a good trade-off, right, between number of variables and the model. So the more variables you have, the less interpretable the thing is. And remember, you want typically to have few features. And if you click on one of those, then you can go to specific metrics, like you can get the ROC curve for that specific model. You can also see the coefficients of the variables, and then you can go back, see other candidate models, select. And at the end of the day, this is useful for an analyst to actually choose features that are meaningful. So the analyst has to validate whether the feature combination looks meaningful, whether they have to, there are some variables that had strange behavior, or things like that. And this is all I have from this part, but I can tell you in a couple of use cases, we found a couple of interesting features that make sense and that were not thought by the analysts in the first place. Okay, so here this is finishing the two examples I had. So learnings we made from that. So we thought about designing tools to make data science projects more efficient. Two of them, as I've shown, one about generic customer attributes and systematic baselines, the other about constructing models, linear interpretable models automatically. So the experience has been positive. So now we have two real tools which are available to data scientists and data engineers in the organization. This is still ongoing work, and the philosophy is a bit experimental, as you see. And the experiment is ongoing. As I mentioned, the real metric here is reusability. But by the way, we have learned a lot in the specific machine learning domains we worked with when we worked on that. And before finishing, I wanted to make a reflection here that also this is a kind of learning we made from that, which is commoditization of machine learning algorithms is a reality. That means you can go to Amazon Web Services, pay, and you buy the latest time series forecasting model they have, okay? Or you can go to Google Cloud and pay for autoML, and they will automate your hyperparameter search and model search. Okay, so you can do that. But what we observe is this works well for mainstream problems, right? So if you have an image classification problem within your project, so it makes sense to use one of these generic tools. Imagine I want to infer the sentiment of a tweet based on the text plus the image. So it makes sense that you pay for one of these services or APIs. Okay. But when our experience and what I have seen, when you work in a data science team which works at that scale, the number of problems, or I would say the speed at which new problems appear, is faster than the speed at which machine learning tools get commoditized. Okay, so these tools are useful to solve the few mainstream problems, but you always have a lot of problems where you need your domain knowledge. So that means you will always need data scientists. Or in other words, the people who are most interested in automating data scientists are actually data scientists, okay? As opposed to some claims that you can sometimes read in the press. And when you have a company like BBVA, which is such a scale, like 140,000 employees and several thousands of employees working in analytics, at least this is the projection for the future, there is still a lot of room for your own projects and commoditizing internally. And this is a buy versus make reflection I always make when I think about that. Thank you very much. Also thanks to these people who provided content. And if you have questions or want to discuss any further, I'll be after lunch at the Data Eng Conf office hours, or you can visit our website and learn more about our projects. Thank you.
Hello.
Hi.
Once you have precise information about people, I'm just curious to know what banks do with that information.
Sorry. You mean we build features for customers? Yes, I'm happy to show you what we do. So this is a tool set we are offering BBVA customers through the BBVA app in Spain. We have several tools where you can show them categorized expenses, you can show them upcoming expenses. So this is just one more use case is, and this is available through the app, so if some of you are from Spain and are customers of BBVA, you will have it. We have the functionality of comparing customers between each other. This is also done by other banks, by the way, in Europe. So you can compare your expenses to similar customers, right? Am I spending too much in this category versus customers who are like me? And the like me can be defined by generic customer attributes, or it could be defined by For instance, this method I just explained, which captures the behavior better. Another example where you use customer attributes is recommendation, recommending products to customers, things like that. I would say, by the way, you can do, banks have been doing that with standard set of attributes, socio-demographic attributes. Here I'm just explaining a way to get a meaningful way of computing customer attributes so that then you can automate all these recommendation engines, right?